representation of a finite group, then its dimension divides the order of the group. So I'd set up the following stuff. I'd introduce some operators Tg on the underlying vector space of the representation for any element of G, although it turned out that Tg was always going to be some multiple of the identity for some complex number. We even had a formula for that. I let R denote the additive subgroup of the complex numbers generated by the elements zeta to the I times lambda G, where the zeta is the primitive nth root of unity. And then we showed that the rational number n over d is in this subgroup R. There was actually a formula for n over d which wrote it as a linear combination of things like that, a z-linear combination. And so the whole proof amounts to showing that the intersection of R with the rational numbers is actually the integers. Since n over d is certainly in R and is certainly a rational number, it will have to be an integer. And that will end the proof. So to do this, I'll prove a series of claims, and here's the most interesting one. This subset R is not merely an abelian group, it's a subring of the complex numbers. It's a subring containing 1, by the way, so it's a subring with unit. Okay. What's the idea? We need to understand how to multiply two elements of this type. So I'm going to show that if I have one of these generators, zeta I times lambda G, and then I have another one, zeta J times lambda H, then that's in R. So this expression is zeta to the I plus J times lambda G, lambda H. Now, zeta to the I plus J, because zeta was an nth root of unity, that's can always be written as zeta to the k, where k is between 0 and n. So basically, I just have to understand this expression, lambda G times lambda H. So I'll show that there's a formula. Lambda G times lambda H always has the following form. It will always be a sum over some elements of the group of mxi times lambda xi, where mxi is an integer. The product of lambda G and lambda H will be an integer linear combination of other lambdas. That such an integer linear combination is certainly in R. If I multiply in the front by zeta k, the whole thing will still be in R. So this will show that R is closed under multiplication. R also has the identity. We can prove that many ways, but in fact, lambda sub identity element turns out to be equal to 1, so that's in R. Zeta to 0 times lambda E is 1. Okay, so how do I show this formula? So remember, the lambda is just the scalar that appears in this formula. So what I'll show is the following. If I take Tg composed with Th, that's a sum over some elements of some integers times Txi. Since these operators are really multiples of the identity, and by the way, this vector space is not zero-dimensional, so you can actually read off what the scalars are. You can read off from this identity the corresponding identity for the scalars. This is really secretly an equation involving scalars, but I'm writing it in terms of operators. By the way here, this sum, as we did last time, that's going to be over a set of representatives of conjugacy classes in the group G. How's this going to work? Well, TGTH is a sum of elements in the conjugacy class of G, phi U, elements in the conjugacy class of H, phi V. The composition of operators is distributive, so I can write this as this kind of sum. Since it's a representation, that's phi uv. So what I'm going to do is I'm going to take this sum and re-index it. I'm going to group together all terms where uv is a particular x. So that's going to be a sum over elements of the group x of phi x, but a bunch of copies of phi x. So mx is going to be a positive integer. What is mx? It's the size of the set, which I'll call capital MX. MX is just the set of pairs consisting of an element in the conjugacy class of G and an element in the conjugacy class of H, such that uv equals x. Basically, I'm just going to collect all the terms involving u and v that multiply up to x, and then I just have to count them. And that's the formula. Okay, so that's a formula for TGTH. But now there's a claim. If x and y are conjugate elements, then those two sets, mx and my, have the same size. You can check this for yourself. I'll just give the argument. The bijection between the sets is given as follows. If y is ax A inverse, then if I have an element uv, which multiplies out to x, then I can conjugate those things by a. Those will multiply out to y, but if the original components were in the conjugacy classes of G and H, so will the new things. And so that's a bijection of sets. So that's why those have the same size. So in this expression, I can group things by conjugacy class. And of course, if I do that, I'll get for each conjugacy class a sum of phi x's over that conjugacy class. So that actually gives me the formula. You could actually go and use this and compute those integers mxi for your favorite group. So we've shown that R is a subring of the complex numbers. It also contains 1, because 1, it turns out, is actually lambda sub e, as you could check. Okay. Now let's go back and think about this abelian group structure. So this was a subgroup of the complex numbers. This abelian group is finitely generated as an abelian group, because we actually wrote it down by writing down a list of generators, and it was a finite set. But it's also torsion-free. Why is that? That's because it's a subgroup of the additive group of complex numbers, and that's torsion-free. There's no non-zero elements of finite order. Therefore, by the structure theory of abelian groups, that abelian group is a free abelian group. It's isomorphic to a product of some finite number of copies of the integers. Incidentally, there's at least one copy, for instance, because we know there's a non-zero element in there. Notice, by the way, that since 1 is an R, the integers are certainly contained in this ring. And of course, that's contained in R intersect Q. We want to show that that occlusion is an equality. So let's suppose I've got a rational number, which is also in R. So I'll call it alpha, but I could also write it as A over B, where A and B are integers, and B is not 0. Now let's let f be the function from R to itself given by multiplication by alpha. That's well defined because R is a ring. And it's a homomorphism of abelian groups because it's a ring. Because you have the distributive law for multiplication. Okay. Now, R is a free abelian group, so we can choose a Z basis. Basis over the integers. Let's call it E1 up through En of R as an abelian group. Now, if I take this homomorphism F and I apply it to some basis element EJ, it's got to be able to be written as some kind of integer linear combination of basis elements. So theCij's are integers. In fact, what I'm doing, if I call this B, I'm taking this homomorphism and writing it in the basis B, and that's a matrix C. That's all I'm saying. And it's an integer matrix. All right, so let's remember now what F is. F is multiplication by this element alpha. Alpha is really a rational number, so it's a quotient of integers. All right, so let's use this to compute F of EJ in two different ways. So on the one hand, I'll copy down the formula. On the other hand, this is alpha times EJ. Can I say something about alpha times EJ? Well, I can, because alpha is a rational number. In fact, it's easiest if I just multiply through everything by b, which is non-zero, remember. B times alpha is the integer a, so that's a EJ. The right-hand side is a linear combination, a z-linear combination of basis elements. That equals that. Because it's a basis, that set of elements is linearly independent, and therefore if these are equal, I can say that the coefficients are equal. In particular, we get an equality of coefficients of EJ, A equals B Cij. Those are all integers, so in fact, A over B is Cij, which is an integer. I'm done. I showed that if my rational number was in R, then it's actually an integer. That's the end of the proof. I've shown that the intersection of R and the rational numbers is the integers. And therefore, this particular rational number in R is an integer. And that's Frobenius divisibility.